Hello everyone. I would like to welcome you to yet another episode of Learning Physics with IBM. I hope it's a beautiful morning wherever you are. And for those studying AS level, today I want to introduce a new unit in the names of thermal properties. And under thermal properties, we are going to see three important areas. For some people, this is called heat, but I prefer to call it thermal properties. Under this unit of thermal properties, I want us to explore ideal gases. We shall explore temperature in details. We shall explore thermodynamics. And actually, we may not follow this order. I may start with ideal gases, followed by thermodynamics, and lastly, temperature. The order depends on the person introducing the unit, but it doesn't actually affect anything. So today, although I have some small cough, I know I will do this better. Today I want us to introduce the unit of ideal gases. You have heard of ideal gases many times, and today I want us to really introduce this. For those, this is specifically for Cambridge AS A level physics. This should be physics 9702. That is paper 4. That's where you'll find concepts of ideal gases. So if you're not doing Cambridge Physics 9702, this may not be of help, but I know in advanced placement, that is AP, you could also find such concepts of ideal gases. Even in other curricula which offer physics at international level, you may find these concepts. So in under ideal gases, we shall be able to explore the equation of state. We shall explore the equation of state, which some people call the equation of the ideal gas equation. We shall explore the kinetic theory of gases. We shall explore the pressure of a gas. And finally, we shall explore the kinetic energy actually, this is the kinetic energy of molecules, or of a molecule. And when we are done with that, then the concepts of ideal gases will now be a part of us. So to begin with, let's have a simple introduction. Under this introduction, we shall look at, or we shall consider two important terms or three important terms that we shall always interact with in this unit. Number one, we shall look at the mole. In not IGCSE, but maybe even in IGCSE or checkpoint, you explored the 7 fundamental quantities, or the 7 fundamental quantities in physics, if I'm to put it like that, where you mentioned length, time, you mentioned mass, you mentioned current, you mentioned amount of substance, luminous intensity, temperature, and the most important quantum I wanted to emphasize here is the amount of a substance. At that level, the unit of the amount of substance was the mole. But then you may not have asked yourself a question, what is a mole? For those doing chemistry, you are used to the mole every day. For those doing MPC, the other is what? MPG. Uh, this might be your first time to see the term mole, but it will appear many times. But for those who have already studied the nuclear physics, the mole is not something new. For those who haven't studied nuclear physics, the mole is simply the amount of substance which contains as many elementary entities, as many elementary units as there are atoms in 12 grams of carbon-12. So the amount of substance which contain the same number of particles, the same number of units, the same number of entities as they exist in atoms, as they exist in, or as the number of atoms which exist in 12 grams of carbon 12 is what we term as the mole. This could be a simple concept for those doing chemistry, but for those doing MPC, I want just to give you a clue about the mole. If I say uh, I have 1 mole of, for example, I have 1 mole of hydrogen, that is deuterium, deuterium, I think it is written as H2, but let me just say hydrogen, H2. I have 1 mole of hydrogen. Oh, I have 1 mole of deuterium, which is H21. That is, if I have 1 mole of deuterium, H21, what does this mean? If I have 1 mole of, say, if I have 1 mole of, say, lithium, Li73, what does this mean? Remember, the mole is the amount of substance which contains as many elementary entities as there are in 12 grams, as there are atoms in 12 grams of carbon-12. So when somebody says, I have 1 mole of deuterium, what does this mean? This means the mass of deuterium which this person has is actually 2 grams. What would be the nucleon number is actually considered to be the molar mass in grams. That means for lithium 73, the molar mass is actually going to be 7 in grams. For those who have seen nuclear physics, this is not a new concept, I'm very sure. So in simple terms, we can simply say that a mole of a substance can be considered as being equal to the relative molecular mass of the substance measured in grams. Now, for those who have studied nuclear physics, I hope you will not confuse this mass in grams with the nucleon number. I mean, or with the mass in atomic mass units U. Because you remember we gave examples in nuclear physics that if you have, for example, helium H42 nucleus, or an alpha particle, which is a helium nucleus, this will be simply the same as the mass of this nucleus will be simply 4U, where you remember 1U was actually 1.66 times 10 power negative 27. You remember that. But then, when we talk about the mole of a substance will simply be considered as being equal to the relative molecular mass of that substance in grams. I've given an example. When I have deuterium, H21, then 1 mole of deuterium is containing or is equivalent to 2 grams. When I have lithium, Li73, then 1 mole of lithium should be having 7 grams. So this is the relative molecular mass in grams. It will be now equivalent to the mole of that substance. Number 2 is Avogadro's number, or sometimes called Avogadro's constant. Now note, this is how we represent Avogadro's constant. It is a capital N and a capital A, but this A is a subscript. Now the mistake we normally make is writing this as if it is sodium Na. This is wrong. Avogadro's number is capital N capital A, but capital A is a subscript. Therefore, do not confuse this. So what do we mean by Avogadro's number? Avogadro's number is the number of atoms contained in 12 grams or 0.012 kilograms of carbon-12, as simple as that. That is Avogadro's number. And experiments have shown that actually uh, 12 grams of carbon-12 or 0.012 kilograms of carbon-12 contains actually 6.02 times 10 power 23 atoms. 12 grams of carbon-12 contains 6.02 times 10 power 23 atoms. This constant is therefore called Avogadro's number, Na. So you will see this many times, or we shall see it, or we shall use it many times. The number of atoms contained in 12 grams of carbon-12 is what we call Avogadro's number. Term number 3, and maybe the last one, is the molar mass, or the relative molecular mass. The mass of 1 mole of a substance is what we call the molar mass. I think the unit of this would be grams per mole. That is called the relative molecular mass. So let's think of a substance which has a simple mass m, and let us think of the same substance whose relative molecular mass is mr. Then we may want the number of moles in that substance, because we said the mole is the amount of substance which contains as many elementary entities as there are atoms in 12 grams of carbon-12. So, how many moles could we be having if a substance has mass m but its relative molecular mass, or the molar mass, is mr? So the number of moles is simply going to be equal to the mass of the substance divided by the molar mass. Because remember, the molar mass is the mass of 1 mole of the substance. Therefore, it means total mass of the substance can be the number of moles times the molar mass. Also remember that the amount of substance which contains as many elementary entities as there are atoms in 12 grams of carbon, as there are atoms in 12 grams of carbon, is called a mole. And yet, the number of atoms in 12 grams of carbon is actually 6.02 times 10 power 23, which therefore implies that the mole could also be represented as, or the number of moles could also be represented as, the number of particles, the number of entities in a given substance compared to the number of atoms in 12 grams of carbon-12, which is Avogadro's number. So many times we shall use this expression here. Number of moles equals to molar mass, mass of the substance over molar mass, which is the same as number of particles, number of atoms, number of nuclei compared to the number of atoms in 12 grams of carbon-12. Let's see some simple but interesting examples. Number one, example number one. Calculate the number of atoms in 12 grams of lithium and calculate the number of moles of lithium. So we want the number of atoms of lithium, which has a mass of 0.3 grams. Number of atoms. So remember, we said the number of moles, N, is going to be equal to the mass divided by the molar mass, which is the same as the number of atoms in a given substance compared to the number of atoms in 12 grams of carbon-12. So since we want the number of atoms in 0.3 grams, I'll take this part of the expression so that N, which is what we want to find, will be equal to the mass divided by the molar mass times Avogadro's number. So it means N will therefore be equal to the mass, that is 0.3 grams, divided by the molar mass, which will be 7 grams, times Avogadro's number, which is 6.02 times 10 power 23. So this will be the number of atoms in lithium 73. When I press my calculator, let me try to press my calculator. You can press yours too. 0.3 divided by 0 divided by 7 multiplied by 6.02 times 10 power 23. So this is giving me the number of atoms in lithium 73 to be 2.58 times 10 power 23. So that is the number of atoms in 0.3 grams of lithium 73. So this is for part A. Then for part B, the number of moles of lithium. So you can take any part that you want, number of moles for lithium. So the number of moles of lithium, number of moles is going to be the mass divided by the molar mass. Without even wasting any time, this is direct. 0.3 grams divide by the molar mass, which is 7 grams. When you press your calculator, 0.3 divided by 7, 0.3 divided by 7. So the number of moles to two significant figures, is approximately 0.043. So that is going to be the number of moles of lithium. So you can also try to verify this. So in conclusion, I'm saying that if we want to find the mass of 1 mole of a particular element, we simply take its nucleon number expressed in grams. The nucleon number in grams. For example, we have seen if I have, for example, uranium-235, uranium-235-92. If I want to find the mass of 1 mole of uranium-235, then I must take the nucleon number of uranium-235 in grams. In other words, 1 mole of uranium-235 will have a mass of 235 grams, because this is the nucleon number in grams. So 1 mole of uranium-235 will have a mass of 235 grams. So I want you to always recall and remember that. Next, let's move, I think, to the equation of state. Move to the equation of state, which is sometimes called the ideal gas equation. The equation of state. So experiments in the 18th century and I think in the 17th century, in the 18th and 17th centuries, showed that the volume, pressure, and the temperature of a given sample are always related. Volume, temperature, pressure of a given sample are always related. Now, these concepts or these quantities, volume, pressure, and temperature, at that time, they were regarded to be macroscopic properties. The word macro means, I think, big, maybe in biology. Macroscopic properties. They were called macroscopic properties by then because they could easily be observed. Just like today, we can easily observe the volume, and actually we can easily measure these quantities. We can easily observe and measure the volume of a given substance. We can easily observe and measure the pressure of a given substance, maybe using a pressure gauge. We can easily observe and measure the temperature of a given substance, maybe using a thermometer. So these are said to be large quantities because they can easily be observed and they can easily be measured using a specific instrument. So these we call them macroscopic properties of a gas. They are called macroscopic because we can easily observe and measure them. They are called macroscopic because we can easily observe and measure them. We can easily observe and measure them using some kind of specific instruments. That's why we are calling them macroscopic properties. So several scientists were interested in one particular property. For example, somebody was so much interested in investigating the volume of a given or the volume of a gas. Somebody was also interested in investigating the pressure of a gas, and somebody was also interested in how the temperature of a gas changes or behaves as some conditions behave. We shall begin with the first person who was interested in one of these properties, and this is Robert Boyle. In I think it's around 1660s. Around 1660, Robert Boyle found that the volume of a gas is inversely proportional to its pressure, provided the temperature is held constant. The volume of So Robert Boyle In 1660, tried to investigate the relationship between volume and pressure of a given gas, of a fixed mass of a gas. And from his experiments, Robert Boyle was able to verify and prove to the world that actually the volume of a fixed mass of a gas is inversely proportional to its pressure, provided the temperature is held constant. Today we call this one Boyle's law. That the volume of a fixed mass of a gas was inversely proportional to the pressure, provided the temperature is kept constant. A process which occurs at constant temperature is said to be isothermal in thermodynamics. Any process which occurs at constant temperature is said to be isothermal. So the volume will be inversely proportional to the pressure of a gas provided the temperature does not change. What does this imply? This therefore implies that pressure times volume should be equal to a constant. To be precise, it would be if a gas is taken through several stages, then we would say that P1 times V1 should be equal to P2 times V2 should be equal to P3 times V3 and so on and so forth. So this one is called Boyle's law, and I'm very certain you studied this in IGCSE. Another scientist in the name of Jacques Charles, between 1746 and 1823, tried to investigate the effect of temperature on volume of a gas. So this French scientist, Jacques or Charles, found out that if the pressure remained constant for a given mass of a gas, the volume was directly proportional to the temperature. As long as the pressure could be kept constant, Charles found out that the volume of a given mass of a gas is directly proportional to the temperature. Today, this is what we call Charles's law. As long as the pressure is constant, any thermodynamic process which occurs at constant pressure is said to be isobaric, or sometimes, anyway, it is called isobaric. Isobaric. The other one was isothermic. This was isothermic or isothermal. The first one at constant temperature was isothermic. So this was temperature constant. What am I writing? Sorry, I have to erase this. So this was isothermic. This was constant temperature. Now this one is going to be isobaric, which is going to be constant isobaric, which is going to be constant pressure. So Charles tried to investigate the behavior of the volume of a gas at constant pressure when the temperature changes, and his observation showed that actually the volume of a fixed mass of a gas V was directly proportional to the absolute temperature, which therefore implies that V over T is equal to a constant, which means if we are taking a gas through several stages, then V1 over T1 could be equal to V2 over T2, which could be equal to V3 over T3, and so on and so forth. So the volume is directly proportional to temperature as long as the pressure remains constant. We are not so much familiar with this in our everyday life. It's hard for people to believe that the volume can increase as temperatures increase as long as the pressure does not change. It's quite abstract. But Remember, the temperature we're talking about here is thermodynamic temperature, which is in Kelvin units. Number three. Number three. Number three is the pressure law. Pressure law, that is according to Joseph Gay-Lussac, between I think that is 1778 and 1815. We normally simply call it pressure law instead of calling it Gay-Lussac's law. We simply call it the pressure law. So Joseph was so much interested in investigating the effect of pressure on temperature as long as the volume is kept constant. And his observation showed that as long as the volume is kept constant, the pressure of a fixed mass of a gas was directly proportional to the temperature, which therefore implies that pressure divided by temperature should be equal to a constant. Or this could mean P1 over T1 could be equal to P2 over T2, which could be P3 over T3. Such a process, which occurs at constant volume, is said to be isochoric or isovolumetric. So this one is sometimes called isochoric, that is constant volume. So such a process which occurs at constant volume is said to be isochoric. So these are actually the basic laws that we really need for this unit of ideal gases, and we shall always be referring to them several times. Remember, the first rule, the first one is said to be Boyle's law, which says that the volume of a fixed mass of a gas is inversely proportional to the pressure as long as the temperature is kept constant. That is said to be Boyle's law. Any process which occurs at constant temperature is said to be isothermic. Then the second law, which is very useful here, is going to be called Charles's law. Charles investigated the relationship between volume and temperature at constant pressure, and his investigations showed that actually the volume of a fixed mass of a gas is directly proportional to the temperature as long as the pressure is kept constant. So all we can do is now to combine these three laws. The last law, according to Joseph K. Lussac, the pressure of a fixed mass of a gas was actually directly proportional to the temperature, provided the volume could be kept constant. So if we combine these three laws, we are supposed to come up with the equation of state. So I'm going to try and combine these three laws. Law number one, volume is inversely proportional to pressure. Law number two, volume is directly proportional to temperature. If volume is inversely proportional to pressure at the same time directly proportional to temperature, you will notice as a mathematician that therefore volume is directly proportional to temperature and at the same time inversely proportional to the pressure. What does this imply? This implies that PV is directly proportional to temperature. That is what it simply implies, which simply implies that PV over T should be equal to a constant. If I remove the proportionality sign, this is for a fixed mass of a gas. PV over T should be equal to a constant. What does this imply further? If the gas is taken through several stages, it is simply implying that PV, P1 V1 over T1 should be the same as P2 V2 over T2 and so on and so forth. So we are therefore saying that PV over T is equal to a constant. This is actually the combination of all these three laws that we have just discussed. So let's fully now manipulate these three laws and come up with a conclusion that we shall basically call the equation of state. Why isn't my eraser working? Sorry. So let me erase all ink at once. So we have now come up with a conclusion from these three that actually PV divided by T is equal to a constant. Now the question will be, what is this constant? PV over T is equal to a constant. What is this constant? Remember, we have been talking about a fixed mass of a gas. So if we use the number of moles, if we use a given number of moles of the gas, then it means PV will be directly proportional to the number of moles of the gas times T, if we use a given number of moles of the gas. So let's now introduce the constant of proportionality. Then it means PV is going to be equal to N times the constant of proportionality R times T. The question will be, what is this R? So R is going to be our constant of proportionality here. By the way, before I go any further, the equation PV equals to nRT is called the equation of state, or it is called the ideal gas equation. So what is R? R is actually called the molar gas constant. The molar gas constant. Sometimes it is called the universal gas constant, simply because it has the same value for all gases. That's why sometimes it is called the universal gas constant. So I want you to note that the volume of 1 mole of a gas at standard temperature and pressure, the chemists know what STP stands for, standard temperature and pressure. The volume of a gas is actually has been found to be approximately, I think that is 0.0, sorry, 0.0, what's wrong, 0.0, 0.02 24 meters cubed. At standard temperature and pressure, the volume of the gas is found to be that, and actually the pressure is found to be approximately 1.014 times 10 power 5 pascals. And I think a standard temperature is that is absolute temperature, that is 273.15 Kelvin. We shall see this later on under temperature. These are the conditions for STP. If we consider these conditions in this equation, then we can establish the constant R. So PV equals to nRT, meaning that R is going to be equal to PV divided by N times T, where P is 1.014 times 10 power 5 pascals. V is 0.0224 divided by N, where N is going to be the number of moles. If I consider 1 mole of a substance, or 1 mole of the gas, N will be 1, then times the absolute temperature, 273.15 Kelvin. When I press my calculator, okay, from my calculator, it gives me R as being approximately 8.3. Why is it hard for me to write using this pen? 8.314 joules per Actually, this is capital K per Kelvin per mole. Of course, this will always be given the list of constants. The molar gas constant or the universal gas constant is given as R equals to 8.314 joules per Kelvin per mole. Sometimes the equation PV equals to nRT will sometimes be quoted as PV equals to nRT. Sometimes you'll find it quoted as PVM equals to RT, where Vm is going to be the actual the molar what? The molar volume. But that one is less common. We can again go further. Now the mathematics can start from here. We play around with the equation of state. Now that we know how we come up with the equation of state, we can go further and play around with it. So from PV equals to nRT, from PV equals to nRT, and we have already seen that the number of moles can also be given as number of moles is given as the number of particles over Avogadro's number of atoms in a given substance compared to Avogadro's number. Then we can combine these two equations so that we come up with the PV being equal to, where there is number of moles, I'll put there N over Na, then times RT. Now a new quantity is going to be redefined here, and this quantity is going to be R over Na. The quantity R divided by Na is going to give us a certain value, which we are going to represent by the letter K. This is small k, not Kelvin. The quantity K is going to be called Stefan Boltzmann's constant. And when you press your calculator, you divide the value of R we got here, divide by Avogadro's number, you'll get K as approximately 1.338 times 10 power negative 23. And the units here will be joules per Kelvin. So it implies that we shall be having PV as being equal to, where there is R over Na, I'll put there K. So this becomes NKT. So sometimes you'll find this equation somewhere in your calculations. Many times you'll find this equation there. Remember, P is pressure, V is volume. P is pressure of a gas, V is volume of the gas, N is the number of molecules, number of atoms in the gas, and the K is called Boltzmann's constant. This is called Boltzmann's constant. K is called Boltzmann's constant. Boltzmann's constant is K. And T is actually the absolute temperature. So we shall always be able to manipulate that equation to that point. So this is the ideal gas equation, or simply that we would call it the equation of state. So this is summarized on this next slide. The ideal gas equation will therefore be given as either PV equals to nRT or PV equals to nKT, and we have seen how we come up with the PV equals to nKT, where P will be the pressure of the gas, P is going to be the pressure of the gas, and V is going to be the volume of the gas, N will be the number of moles of the gas, that is small n, then R is going to be the molar gas constant, which is 8.31 times 8.314 joules per Kelvin per mole. T is going to be absolute temperature, that will be temperature in Kelvin units. N is going to be the number of molecules or atoms of the gas, and K will be Stefan Boltzmann's constant, or simply called Boltzmann's constant, which is sometimes I think it's given in the list of formula, but can always be found from R divided by Avogadro's number. Since we have already seen that R is 8.314, and I'm sure that is always given, and Avogadro's number is 6.02 times 10 power 23, which is also given. This will always give us the value of K without any problem. Now, there are a few things that we need to point out from this, from what we have just seen. Number one, the laws we have been talking about, Charles's law, Boyle's law, to mention pressure law too. These, strictly speaking, are not going to be real laws. The laws of Boyle, Charles, and Gay-Lussac are not really laws, as their validity is restricted. They are not valid under all conditions. They have some restrictions. The laws are accurate for real gases only if the pressure of the sample is not too great and if the gas is well above its liquefaction temperature. That is, it remains a gas at a temperature where it is supposed to be a liquid, or where it is supposed to be liquidified, which is practically almost impossible. However, we can use these laws, we can use Boyle's law, we can use Charles's law, we can use Lussac's law to define what we call an ideal gas. Now, the word ideal is coming in. Everyday in your class situations have always talked about the word ideal. Something is ideal. It's ideal that every student scores an A star in physics. It's quite ideal. Although it is possible, but it's quite ideal. So ideal could be practically it is not achievable, but we can always have approximations. So it is very impossible or almost impossible to use to to apply these laws onto real gases unless the pressure of the gas is not too great, not too high, and yet the gas is existing as a gas above its liquefaction temperature. Since such a condition or such conditions are practically not easy to achieve, then such gases are referred to as ideal gases. So what do we mean by an ideal gas? The question will be define an ideal gas. An ideal gas is going to be defined as a gas which obeys the equation of state. That is the equation PV is equal to nRT at all temperatures, pressures, and volumes, where in that equation we shall have to define all the quantities. P is pressure of the gas, V is actually the volume of the gas, T will be the thermodynamic temperature, R will be the molar gas constant, and N is the number of moles of a fixed mass of a gas. So that is an ideal gas. It obeys the equation PV is equal to nRT at all temperatures, pressures, and volumes. You define all the quantities. But of course, it doesn't mean that we are going to discard these laws that we have discussed. We may not discuss the laws of Boyle, Charles, and Gay-Lussac, but then every time we shall be using them on gases, we shall be assuming that the gas is behaving as if it was ideal. That is, the gas is existing as a gas at a temperature at which it would liquefy, and yet the pressure is not too high. So, every time we use the ideal gas equation PV is equal to nRT on a gas, we shall always be assuming that the gas is behaving as if it is ideal, because these laws that we have mentioned have restrictions. They cannot be applied at any temperature or at any pressure. They are only applied to a gas whose pressure is not so high, but yet the gas exists as a gas at a temperature it would be a liquid. So for calculations and for approximate calculations, you'll always see us or you'll always see me using the ideal gas equation. But every time I use the ideal gas equation on any gas, have it in mind that I'm just assuming that the gas behaves as if it was ideal. Let's do a few examples. Example number one. Example number one. Find the volume occupied by 1 mole of air at STP. Remember, STP stands for standard temperature and pressure. Find the volume occupied by 1 mole of air at STP. Taking, of course, STP, they have given us the temperature to be 273, the pressure to be 1.01 times 10 power 5, the molar gas constant as 8.3 joules per Kelvin per mole for air. So we want to calculate the volume occupied by 1 mole of air at STP. So assuming air is behaving as an ideal gas, then we can simply say PV is equal to nRT. So we want to find the volume. So volume is going to be equal to nRT divided by the pressure. Number of moles is 1. Molar gas constant 8.3. Temperature is 273 divided by the pressure, which is 1.01 times 10 power 5 pascals. So this will give us the volume. I press my calculator. I think without even calculation, I know this is standard temperature, this is standard pressure, this is molar gas constant, then the volume should be standard volume, which is approximately 2.24 times 10 power -2 in meters cubed, or 0.0224. Okay, I think that is very obvious. This is very easy. I can't spend much time on it. Number two, question number 2, or example number 2. Find the number of molecules per cubic meter of air at standard temperature and pressure. So we know the standard temperature, we know the standard pressure. We want the number of molecules. We want the number of molecules per cubic meter of air at standard temperature and pressure. Remember, 1 mole of air at STP, we have already seen this in the previous example. 1 mole of air at STP has a volume of, we have just calculated this, 2.24 times 10 power -2 meters cubed. That's 1 mole. But remember, 1 mole of a substance, 1 mole of a substance, 1 mole of a substance is equivalent or contains 6.02 times 10 power 23 entities. Call them molecules, call them atoms, call them whatever you want, and this is Avogadro's number. That is Avogadro's number. So it implies that this volume, which is 2 because 1 mole of air has this volume, and yet 1 mole contains this number of atoms, particles, or molecules. So it means 2.24 times 10 power -2 meters cubed should be having this number of molecules or atoms. But we want the number of molecules per cubic meter, that is in 1 cubic meter. So 1 cubic meter should be having 6.02 times 10 power 23 divided by 2.24 times 10 power -2 molecules. So when you press your calculator, when I press my calculator, I get the number of molecules per cubic meter to be 2.69 times 10 power 25 molecules. So 1 cubic meter, or the number of molecules per cubic meter of air, is 2.69 times 10 power 25. I think that is easy. Let's go to the next example. Example number 3. Example number 3. A syringe contains 25 times 10 power negative 6 meters cubed of helium gas. So this is the volume at temperature of 20 degrees Celsius and the pressure of that. The temperature is increased to 400. So we have changed from 20 to 400 degrees Celsius. And the pressure on the syringe is increased to this. So there has been a change in pressure. Find the new volume of the gas. So volume is changing, temperature is changing, and pressure is also changing. Assuming the gas behaves as if it is ideal, then we shall say that PV is equal to nRT. If the gas is behaving as if it is ideal, then PV is equal to nRT, or P1 V1 over T1 should be equal to P2 V2 over T2, because after all, N and R will remain as constants. So we want to find the second volume V2. So it means V2, volume V2 will be equal to P1 over P2 times T2 over T1 times the volume V1. I'm now substituting. The reason as to why I've written these fractions is because I suppose the units will change, but the units of temperature will not change by dividing. They must be converted. So I'm now substituting pressure. The first pressure is 5.0 times 10 power 4 pascals divided by 2.4 times 10 power 5 pascals. The temperature must be in Kelvin units. T2 will be 400 plus 273 divided by T1 is 20 plus 273. So that will be the temperature. Then I multiply this by the first volume, which is 25 times 10 power negative 6. So I pick my calculator, V2 5. So this is times 10 power 5. Okay, so when I press my calculator, I get the volume V2 as 12 times 10 power negative 6 meters cubed. So there has been a decrease in the volume. There has been a decrease in volume. After all, we know that when the temperature, we know that volume is directly proportional to temperature. At the same time, volume is inversely proportional to pressure. Volume is directly proportional to temperature. At the same time, volume is inversely proportional to the pressure, just from these expressions here. So you can now verify that the new volume V2 is most likely going to be that. Please note very carefully that every time you have the temperature in degrees Celsius, let it be part of you that you always have to remember to convert from degrees Celsius to Kelvin units. You must always convert from degrees Celsius to Kelvin units. And you have seen that to convert from degrees Celsius to Kelvin, you should add 273. If you are converting from degrees Celsius to Kelvin, you should add 273. We shall see that under temperature. Next, example number 4. Example number 4. Here we have two containers. The containers are filled with an ideal gas. That means PV is equal to nRT. Calculate the total amount of gas in mole in the containers. The pressure of the gas is 2.3 times 10 power 5 pascals. So this in container A, we have a volume of this, we have a temperature 17 degrees Celsius, which will be 17 plus 273, 17 plus 273, which is I think 290. So this temperature is 290 Kelvin. The other one we have 30, so 30 plus 273. So this temperature is 303 Kelvin. So calculate the total amount of gas in moles. In other words, we want the number of moles. Remember, for an ideal gas, PV is equal to nRT. So the number of moles or the amount of gas in moles is going to be PV divided by R times T. So using one of the containers, I'll use the first one. I will use container A because the question is saying calculate the total amount of gas. So let me first find A. For container A, this will be pressure. The pressure is 2.3 times 10 power 5. The volume is, we are converting from centimeters cubed. We are going to convert from centimeters cubed to meters cubed. And when you convert 3.1 times 10 power negative 3, positive 3 to meters cubed, you multiply by 10 power negative 6. So this becomes 3.1 times 10 power 3. Again, we multiply by 10 power negative 6 to change it to meters cubed. We divide this by 8.314, which is the molar gas constant. Multiply this by the temperature, which is 290. And we get our answer there. You can also press. Then for B, we shall do almost the same thing. Our volume, the pressure is 2.3 times 10 power 5 pascals. Then we multiply this by the volume, which is 4.6 times 10 power 3. We multiply by 10 power negative 6 to change the volume to meters cubed. Divide by 8.314 times the temperature, which is 303. So if you have pressed your calculator here, this is 2.3 times 10 divided by times 290. So I am getting to three significant figures, 0.296 mole. Then for the second one, I just change that. And I'm getting a 0.420 mole. So the total number of moles is going to be the sum of those two. When you sum up, you get 0.716 moles as the total. So that is the total amount of the gas in moles in the containers. Number 5. So number five, helium 4 may be assumed to behave as an ideal gas. A cylinder has a constant volume 7.8 times 10 power 3 centimeters cubed and contains helium 4 gas at a pressure, so this is the pressure, 2.1 times 10 power 7, and the temperature is 290 Kelvin. Calculate for the helium gas the amount of gas in moles. So we want number of moles. So now we know number of moles N is going to be the pressure times volume, that is PV. My handwriting is not appealing. So number of moles is going to be pressure times volume divided by R times T. I just made the N the subject. So when we substitute, we are substituting 2.1 times 10 power 7 multiplied by the volume 7.8 times 10 power 3, but remember we have to change it to meters cubed times 10 power negative 6, divide by the molar gas constant 8.314 times the temperature in Kelvin units, which is 290. Then you simply press the calculator. So when I press my calculator, I get 68 moles. We can also deduce the number of molecules of the gas. Number of molecules, remember, number of moles is equal to mass over molar mass, which is the same as number of molecules or number of atoms in the gas or compared to Avogadro's number Na. Since I want N, so number of molecules will be equal to the number of moles times Avogadro's number, which will be 68 times 6.02 times 10 power 23. You press your calculator, 68 times 6.02 exponent 23. The number of molecules of the gas will be 4.09 times 10 power 25. That is to three significant figures. That would be the number of molecules. If I wanted the mass of the gas, still I will do the same thing. From this expression, I will say that the mass is equal to the number of moles times the molar mass. As simple as that. So this would be 68 times the molar mass because it is helium-4. So this would be 4 in grams, of course. So this will give me 68 times 4, which will give me 272 grams, because this is molar mass in grams. As simple as that. Okay, next example 6. May you go to example 6. Initially, tap T is closed. The cylinders contain an ideal gas at different pressures as shown above. So tap T is initially closed and the pressures are different. Show that cylinder A contains 0.34 mole of gas. That is easy. Number of moles is the same as PV divided by R times T. We just substitute. The pressure there is 3.4 times 10 power 5. The volume there is 2.5 times 10 power 3. Multiply this by 10 power negative 6 to change from centimeters cubed to meters cubed. Divide this by the molar gas constant, which is 8.314. By the way, many times it is quoted as 8.31, so don't get confused. Times the temperature in cylinder A is 300 Kelvin. Then we press our calculator. Calculator 3.4 exponent 5 times 2.5 exponent negative 3 divided by 8.314 times 300. So this is giving me 0.34 to two significant figures. So that is the number of moles or the amount of the gas in cylinder A. Then part B. So we need to quote the volume of cylinder A, the pressure, the temperature. Volume of cylinder B is this, the pressure is this. I think part B may want us to find the temperature of cylinder B. Let's check. So we know the pressure of cylinder B 3.9 exponent 5. We know the volume 1.6 exponent 3 centimeters cubed. Cylinder B has a constant volume of 1.6. Cylinder B has a constant volume of 1.6 exponent 3 and contains 0.2 mole of gas. When tap T is opened, the pressure of the gas in both cylinders is 3.9 times 10 power 5. That means the pressure of the pressure of cylinder B becomes the pressure of the gas when the tap is opened. So they are saying no thermal energy enters or leaves the gas. By the way, such a system where no thermal energy enters or leaves the gas is said to be adiabatic. Such a system where no thermal energy enters or leaves the gas is said to be adiabatic. There is no heat exchange with the surrounding. No heat enters or leaves the system, so it is said to be an adiabatic process. No thermal energy enters or leaves the system. It is said to be an adiabatic process. So, determine the final temperature of the gas. So we want to determine the final temperature of the gas. Okay, I think that is also easy. So PV equals to nRT. We can find the total number of moles. So PV equals to nRT. So we are going to find total number of moles of the gas. We have already the number of moles of the gas which was in cylinder A. All that we are remaining with is the number of moles of the gas in cylinder B, which was even given as 0.2. So the total number of moles of the gas is going to be 0.34, which you obtained for A plus 0.20. This gives us a total of 0.54 moles. So that is the total number of moles of the gas in the two cylinders. Then we now want temperature. From temperature equals to PV, that is pressure times volume, divided by NR. I will find the total temperature when the tap is opened. So this would be, since the pressure is 3.9 times 10 power 5 pascals, total volume being a scalar, we just sum up total volume. We are adding this volume to the other first volume, which was 3. The volume of cylinder A was 2.5. So when we add 2.5 times plus 1.6, we get, I think, 4.1 times 10 power 3 multiplied by 10 power negative 6 to change it to meters cubed. Then we divide this by the number of moles, total number of moles, which is 0.54 times the molar gas constant, which is 8.314. This is going to be equal to, press the calculator, 3.9 exponent 5, 4.1 exponent negative 3 divided by 0.54 times 8.31. Okay, so to two significant figures, rounding off to two significant figures, I'm coming up with 360 Kelvin as total, the final temperature of the gas when the tap is opened. Now when you compare the initial temperature of the gas, which was 290 in one of the, 300 in one of the cylinders, and when you compare the new temperature is above 300 Kelvin, meaning that the temperature of the one cylinder, that is cylinder A, has actually increased. So the question in part C is saying, by reference to work done and change in internal energy, we are going to see internal energy later on under thermodynamics, suggest why the temperature of the gas in cylinder A has changed. Why has the temperature of the gas in cylinder A changed? by reference to work done and change in internal energy suggests why the temperature of the gas in cylinder A has changed. Why the temperature of the gas in cylinder A has changed. In other words, it has actually increased. So one, you will notice that when the tap is opened, remember cylinder B is at high pressure than cylinder A. What does that mean? Gas is passed, gas is going to be passed, or gas passes or is passed from cylinder B to cylinder A. When the gas is passed from cylinder B to cylinder A, because B is at high pressure, it means work is done on the gas in cylinder A. Work is done on the gas in cylinder A. Work is done on gas in cylinder A, but remember there is no heating. No heat enters or leaves the system. Yet work is done on cylinder A. It's like compressing a piston. You are doing work on the gas which is trapped by the piston. And if work is done on the gas, it means the volume decreases. It means the volume of the gas which was in cylinder A is supposed to decrease because work is being done on that gas. And if no heat enters or leaves the system, the only option which remains is the temperature to increase. So work is done on the gas in the cylinder, but remember no heat enters or leaves the system. Sorry. Work is done on the gas in cylinder A, and since no heat enters or leaves the system, it is the internal energy which we are going to explore in details next. Internal energy and hence the temperature. Internal energy and hence the temperature increase. We shall see that temperature is the average kinetic energy of the molecules which make up the system temperature. Especially if the system is an ideal gas, temperature is the average kinetic energy of the molecules that make up the ideal gas. Later on, we shall still see that internal energy is the sum of the potential and the kinetic energies of all the molecules or atoms which make up the system. So, if gas is passed from cylinder B to cylinder A, where B is at high pressure than A, then it's like a gas in B is doing work on the gas in cylinder A. Therefore, because there is work being done on cylinder A, the internal energy or the total kinetic and potential energy of the molecules in cylinder A does what? Increases. And if the kinetic energy of the molecules in cylinder A increases, the temperature has increased because temperature is the average kinetic energy of the molecules which make up the system. Okay, I hope I've tried my level best to answer that question. Let's go to the next example. Example number 7. Argon 40 may be assumed to be an ideal gas, a mass of 3.2 grams. 3.2 grams of argon 40 has a volume of 210 centimeters cubed at a temperature of 310 degrees Celsius. Determine for this mass of argon the amount in moles. So that is very easy. Number of moles is equal to PV over R times T. We substitute. We have the pressure, we don't have the pressure, we have only the volume, we know R, we know T. So this may not be a good equation to use, but still, number of moles can also be mass over molar mass, where the mass is 3.2 grams divided by the molar mass, which is 40 grams, because the molar mass is the relative molecular mass in grams, When I press my calculator, 3.8, 3.2 divided by 40, that is 0.08. So the number of moles of argon is 0.08 mole. Then, so this was part A. Part B, the pressure. Now I can use this expression very easily because I know pressure and number of moles is PV over RT. So the pressure is going to be number of moles times RT divided by the volume. I'm now substituting. The number of moles is 0.08. Molar gas constant is known 8.314. Temperature should be in Kelvin units. Remember, the temperature should be in Kelvin units. So that would be 310 plus 273 Kelvin divided by the volume, which has been given as 210 centimeters cubed. So this should be 210 times 10 power negative 6 to change it to meters. So let's press our calculator. 310 plus 273 times 8.314 times 0.08 divided by 210 exponent negative 6. So I am getting a pressure which is quite surprising, 1.85 times 10 power 1.85 times 10 power 1 power 6 pascals. You can also check by calculation, you can also check. But that is literally the pressure that I'm getting. Next should be number 8, I guess. Number 8. A constant mass of an ideal gas has a volume of 3.49 times 10 power 3. Temperature 21.0 degrees. When the gas is heated, 565 joules of thermal energy causes it to expand to a value of this at this temperature. This has been illustrated here. But the question is saying show that the initial and final pressures of the gas are equal. Show that the initial and final pressures of the gas are equal. So they are telling us at a constant mass of an ideal gas has this volume at that temperature. When the gas is heated, this amount of energy is supplied. It causes it to expand to this volume at that temperature. Show that the initial and final pressures of the gas are equal. That is actually showing that pressure is constant. When pressure is constant, volume is directly proportional to temperature. So simply we know that V over T should be equal to constant. V1 T1 over T1 should be equal to V2 over T2. All we need is to verify if V1 over T1 is the same as V2 over T2. If they are equal, then the pressure is constant. So this is actually Charles' law. Volume is directly proportional to temperature at constant pressure. So let's verify. Let's start with the first one. Let's find V1 over T1. I'm substituting simply. V1 is, I may not even convert the units, but if you want, you may convert, no problem. 3.49 times 10 power negative 3 times negative 6, power 3 times negative 6 becomes negative 3. Divide by the temperature in Kelvin units, that is 294. Press the calculator. So to three significant figures, I'm getting 1.19 times 10 power of negative 5. That is V1 over T1. Let me check V2 over T2. V2 over T2 will therefore be 3.87 times 10 power. When I change from centimeters cubed, it becomes negative 3. Divide by the temperature in Kelvin units, which is 53 plus 273. 53 plus 273. So divide by 326. So divide. So when I divide to three significant figures, I'm getting 1.19 times 10 power negative 5. So if V over T is the same, then it means it is a constant. Then the pressure is constant. So we can simply conclude by saying that since V1 over, where was I? So we shall conclude by saying that since V1 over T1 is equal to V2 over T2, which is 1.19 times 10 power negative 5, and it is a constant, then pressure is constant. So we have verified that the pressure of the gas, or pressures of the gas, are constant. Okay, part B. The pressure of the gas is 4.8. 4.2 times 10 power 5. For this heating of the gas, calculate the work done by the gas. For this heating of the gas, remember some energy has been supplied in the heating so that the temperature changes from 21 to 53. So for this heating of the gas, calculate the work done by the gas. I think we can see that the gas is doing work because it is expanding. The first volume was 3.49 exponent 3. The second volume is 3.87 exponent 3. So there has been an expansion. So for this heating, calculate the work done by the gas. We saw this in AS. Work done by an expanding gas is given by the work done by an expanding gas in AS. We saw that is pressure times change in volume. Since there has been a change in the volume, then there is some work done. So the pressure is 4.20 times 10 power 5 pascals. And the change in volume is actually the difference between 3.87 minus 3.49. This will be times 10 power negative 3 if I change it direct to meters cubed. So it is times 10 power negative 3. When you press your calculator, pressing the calculator, it gives me approximately 160 joules to two significant figures. 160 joules. Use the first law of thermodynamics and you answer in Roman 1 to determine the change in internal energy. We shall see this in our next unit, but for now, for completeness, the change in internal energy, delta U, is equal to the amount of heat supplied plus the work done. If the heats, we are going to see some sign conventions. If the heat is added to the system, Q is positive. If work is done on the system, W is positive. But if the system does work, W is negative. If the system loses heat, Q is negative. So since the gas is doing work, it is expanding because there is an increase in volume, then W will be negative. So when we substitute, Q is given as 565 minus 160. Note this minus here. The first law of thermodynamics states like this. Change in internal energy is equal to Q plus W. But it has what we call sign conventions. When heat is added to the system, Q is positive. That is a sign convention. A convention is a rule. When the system loses heat, Q will be negative. When work is done on the system, W is positive. But since the work is done by the system because it's expanding, W is negative. Now this gives us a change in internal energy of 406.5 joules. And if the change in internal energy is a positive value, then this is an increase in internal energy. If it was to be a negative value, then we would call it a decrease in internal energy. You will see those sign conventions later on in details. Lastly, on part number 8, explain why the change in kinetic energy of the molecules Explain why the change in kinetic energy of the molecules of this ideal gas is equal to the change in internal energy. Why is the change in kinetic energy of the ideal gas equal to the change in internal energy? So remember, this is an ideal gas. We have said an ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. But what do we know about an ideal gas? Later on we shall see the ideal gas in details, and we shall see that for an ideal gas, the molecules are infinitely far from each other, that the potential energy due to the forces of attraction between the molecules is negligible. Therefore, for an ideal gas, internal energy or the change in internal energy, delta U, or internal energy is simply equal to the sum. We know that internal energy is the sum of the kinetic energy and the potential energy of all the molecules which make up the system. But for an ideal gas, there are no intermolecular forces. And as long as there are no intermolecular forces, or the intermolecular forces are negligible, it means the potential energy component becomes zero. So potential energy is zero for an ideal gas. And if the potential energy is zero, yet internal energy is the sum of kinetic energy and potential energy, then it means that internal energy is only going to be equal to the kinetic energy of the molecules. Note this analysis very well. Internal energy of a system is the sum of the random distribution of the kinetic energies and the potential energies of all the molecules which make up the system. But if the gas is an ideal gas, the molecules are so far from each other, infinitely far, that the intermolecular forces are negligible. And if the intermolecular forces are negligible, potential energy depends on those intermolecular forces. But if they are negligible, it means potential energy is also negligible. Therefore, we remain with kinetic energy being the only component or the only part contributing to the internal energy of an ideal gas. You must mark that very, very carefully. Okay, next, example number 9. Example number 9. So the variation with volume V of the pressure P of an ideal gas is as it undergoes a cycle ABCA of changes is shown below. So we can see that the temperature, let me check the next slide. The temperature of the gas at A is 290. The temperature at B is 870. Determine amount in mole of the gas. The temperature of the gas at C. Explain why the change from C to A involves external work and a change in internal energy. So let's mark these values. At A, the temperature is 290. At B, the temperature is 870. And we are going to find the amount in moles, in other words, the number of moles. We shall find the temperature at C. We shall come to the explanation later on. So the temperature at A has been given as 290 Kelvin. We have noted that. The temperature at B has been given as 870 Kelvin. So we want to find an amount in mole of the gas. So the same gas is taken through stages. So we can still find the number of moles. Number of moles is going to be PV over R times T. We are going to consider A. We can consider A. You can also consider B. You'll get the same answer. If I consider point A or stage A, pressure is 1.2 times 10 power 5 pascals. 10 power 5 pascals. The volume here is 4 times 10 power negative 3 meters cubed. Molar gas constant 8.314. The temperature at A is 290. We press our calculator to get the number of moles. So the number of moles is 0.20 mole to two significant figures. You can check yours. You can also check the same at B. Let's verify at B. So this one I used stage A. Because it's the same gas, then the number of moles is going to be the same. So number of moles is going to be sorry. Let me write here. The number of moles I'm considering B. The number of moles is going to be equal to P, pressure is 3.6 times 10 power 5 pascals. Volume is at B, it is still 4 times 10 power negative 3. Negative 3 divided by molar gas constant 8.314 times temperature at B, which is 870. So when you press your calculator, so to two significant figures, I'm getting the same thing, 0.20 moles. So at B, you'll get the same thing. Then calculate the temperature of the gas at C. Now that I know the number of moles, I want the temperature. I'll use the same formula, but this time the temperature will be equal to pressure times volume over number of moles times R. So at C the pressure is 1.2 times 10 power 5. The volume at C is 7.75 times 10 power negative 3. Number of moles is going to be 0.20 times the molar gas constant. Molar gas constant is 8.314. So we press our calculator to find the temperature at C. So the temperature is 560 Kelvin as the temperature at C. So temperature at C is 560 Kelvin. So the next question was telling us to explain why the change from C to A involves external work. Why the change from C to A involves external work and a change in internal energy. When you understand internal energy, it will be easier for us to explain such, but it's very easy. So one, look at the change from C to A. The change from C to A is involving a decrease in volume. That means work is done on the system. So the volume changes, that is, the volume decreases. Volume decreases. That is from C to A. The volume decreases, and if the volume is decreasing, it means work is done on the system. So work is done on the gas. That is one. That's why we have a change. That's why we are saying external work is it is involving external work. The volume of the system of the gas is decreasing, meaning that the work is done on the gas. Number two, they said explain why the change from C to A involves external work and a change in internal energy. There is also a change in internal energy because at C the temperature is 560, at A the temperature is 290. So the temperature decreases. The temperature decreases. And if the temperature decreases, it means energy leaves the system. So internal energy decreases. The temperature decreases, so internal energy decreases because the temperature decreases. However, if we started from stage A to stage B to stage C and back to stage A, the total change in internal energy for the gas when we come back to stage A, the total change in internal energy would be 0. Because if we started from stage A where the temperature is 290, stage B it becomes 870, stage C it becomes 560. Coming back to stage A where it is 290, we are coming back to the same temperature. If the initial temperature is the same as the final temperature, then the total change in internal energy is 0. That means if the final temperature is equal to the initial temperature, then there is no total net change in internal energy. There will be no net change in internal energy. It doesn't mean that there is no change in internal energy from C to A. Actually, you will find that there is a decrease in internal energy from C to A. You would find that there is a decrease, there is actually an increase or a decrease in internal energy from B to C. But if the final temperature at a given point is the same as the initial temperature, then the total net change in internal energy would be 0. So to answer this question, which is in part C, to answer the question in part C, which was telling us to explain why the change from C to A involves external work and a change in internal energy, we have said 1, the volume decreased and the temperature also decreased. The volume at C was 7.75, at A it was 4 times 10 power negative 3. So there's a decrease in volume, so work is done on the system. It's like compressing a balloon. The volume decreases, it means you are doing work on the balloon, or on the gas in the balloon. Then change in internal energy, the temperature at C was 560 and at A it is 290. Since there is a decrease in temperature, then there is a decrease in internal energy because it means energy is leaving the system. I think at this point you qualify for a self-check. Self-check. Check yourself and test yourself with the following questions. Self-check. Number 1, a mass of carbon dioxide occupies this volume, that temperature, that pressure. What will be its volume at this temperature and that pressure? Calculate the number of moles, calculate the number of molecules of the gas. Number 2, a volume of 250 centimeters cubed trapped in a cylinder closed by a smooth piston at a pressure of 1.2 times 10 power 5 pascals. The piston is pushed in slowly until the volume of the gas is 150. What is the new pressure? Then lastly, you have two flasks having equal volumes connected by a narrow tube with a tap which is closed. The pressure of air in one flask is double the other. After the tap is opened, the common pressure is 120 kilopascals. Find the number of moles of the gas used if volume of each flask is 5.6 at a temperature of 20 degrees Celsius. Then next, the original pressure in the flasks. The original pressure in the flasks. On addition to this, this could be number 13. You are going to define the following terms: isochloric, isothermic, adiabatic processes. So you are going to also define an isochoric process, an isothermic process, and an adiabatic process, as explained in this lesson. I guess it's better if we stop here for today, and I wish you a good day. Do not forget attempting this self-check. Submit it under any platform you want. You can submit it on Teams. You add it to your one notebook on Teams, or you can just forward it to me in any form you want. Deadline is tomorrow midnight. Otherwise, have a good time and enjoy your holidays. Bye bye for now.